I think now
Let's
we can
start.
start.
Yeah.
Should we start?
Dr. Reshma, yeah, let us start now.
Okay. Yeah. Good evening, everyone.
Good.
A very warm and pleasant welcome to all the members of NASNI who are present, students, astronomy enthusiasts who have joined us today for this online session. And on behalf of NASNI, it really gives me a pleasure to welcome you all to the 24th online talk organized by National Astronomy Network of IIPT. And today's talk is on the topic Astronomy 2025 Highlights, Insight, and Future Directions by Dr. DrPriyaHasan. Before I invite ma'am to deliver the talk, let me just say a few things. NASNI has always been committed to promoting astronomy education. And I must say today's talk is another step in the direction. And as we conclude the year with an exciting journey into the astronomy. This today's talk aims to connect the scientific community, or this lecture series also of NASNI, connect scientific community and the amateur astronomers with leading experts in astronomy and astrophysics, offering insight into very recent discoveries, ongoing research, and future prospects. Now, this talk is particularly special as it focuses on latest development in astronomy in 2025, offering both a retrospective and a forward-looking perspective. Let me briefly introduce distinguished guest speaker today, Dr. DrPriyaHasan. Dr. DrPriyaHasan did her integrated master's in physics, specializing in astrophysics from the Moscow State University, Moscow, Russia, in 1996. She did her PhD in astronomy at Osmania University, Hyderabad in 2004. She did her postdoctoral research in France and also IUCAA, Pune. She was awarded the Women Scientist Award by the Department of Science and Technology. The US Consulate in Hyderabad selected her for the International Visitors Leadership Program in 2011 to visit and deliver lectures at select universities in US like MIT, Harvard, Caltech. She presented her work in various conferences in India as well as other parts of the world. Her research interests are in observational astronomy, in star formation, clusters, and galaxies. She's a member of international science-driven team of the 30-meter telescope. Dr. Priya is actively involved in Olympiads, public outreach, and science popularization programs for children and adults, and has worked on various projects with IAU, OAD, US Consulate, Hyderabad, etc. At present, she is an assistant professor in physics at Maulana Azad National Urdu University, Hyderabad, and she is also the co-chair of the Women in Astronomy Working Group of the International Astronomical Union. She was the secretary of Public Outreach and Education Committee of Astronomical Society of India, and presently she is also regional astronomy the coordinator of astronomy education. Today's topic and future direction. With this brief introduction, I will invite and request Dr. DrPriyaHasan to kindly take over the session and enlighten us with her talk. Welcome, ma'am, to this session.
Thank you so much, Dr. Reshma Desai. Thank you so much, NASNI, for inviting me. I'm really very happy to get this opportunity to speak over here on this platform because NASNI is really doing good work in promoting astronomy to people with these regular talks which are conducted so regularly, and I'm sure people are benefiting a lot from it. So thank you so much. Thanks for inviting me. So when I was invited to give this talk, I was very ambitious in the sense which you can see from my title, which is Astronomy 2025, Highlights, Insights, and Future Directions. Because today is the great day where we conclude our year, and I'd be ending with wishing you for a happy new year. And that's why I thought that this is the right kind of talk to have on the 31st, where you want to kind of wrap up for the year. But then obviously, when you kind of think of the year, there are so many important things which did happen that it's obviously very difficult to cross through everything. So I've actually selected a few select things which are at various scales, so that it touches upon different scales. And I hope it, it kind of covers it. But obviously, there are certain areas which I have dropped, and forgive me for that. So this has been a very interesting year, and let's start off with this thing. So the usual events which you are all aware of, is which we have our astronomy events, is, for example, you have meteor showers. Many of you all could have seen the Geminids, which were very recently there. The Quadrantets, the Lyrids, the Perseids, there are various interesting, meteor showers, which are definitely good fun to see. There are eclipses. This year we had a total lunar eclipse on September 7th and a partial solar eclipse. And then we had planetary events like a Mars opposition and various things. So with astronomy, the show always goes on. There's always something fun in every month, which you can always have a look at, and you can, there's always something interesting to see up there in the skies. So those are obviously there. But today we'll be talking about some new discoveries and a little bit about next generation observatories and instruments. I will not be able to, because of time constraint, I will not be able to cover everything. I'm just covering some aspects of it. And each of them would actually require individual talks. So we do it sometime later. Okay. So like I said, because of this ambitious title which I had, the question was, how do we cover it up? So what I'm going to do is I'm going to select 4. There are basically 4 at different scales, which I'm going to talk about. Select 4 of astronomical discoveries, which I would think are the highlights for this year. Okay, and they give you good understanding in various aspects of astronomy, and hence they are worth talking about. So let's start off with our first thing. You must have heard about this thing, about a second moon, right? So sometime back, you must have seen that in the news, where there was a declaration that NASA has confirmed that we have a second moon, and the second moon is until the year 2083. So this is what I'd call Earth's fickle companion. A fickle companion is a temporary companion, because this is our temporary companion, which was discovered this year. And let's actually see what this actually means when you say that the Earth has a second moon, right? So what does this actually mean? So this object was actually called 2025 PN7. PN7 because this is from the Pan-STARRS. This Pan-STARRS is a 1.8 meter telescope, which you can see over here. And it has a massive camera. The camera is the biggest highlight of this telescope, which is a 1.4 gigapixel camera. And basically what it does is it studies a very wide field of view of the sky. Okay, and the purpose of this camera is basically to detect asteroids, comets, variable stars. So these are what we call transients. Okay, transients in the sense variables, objects, right, which are there in the sky. And basically what this does is basically searches for such objects. Okay, that is the job of the Pan-STARRS telescope. So the Pan-STARRS telescope, it discovered, I can show you, what it actually found was this. If you actually see, I'll show that for you in another one. So what they actually found is this moving object. You'll see it in a while for another object, which was called 2025 PN7. And they found that this was an object which was actually going along with the Earth around the sun. Okay. So this object, it had an aphelion of about, so you see it's about the distance of the Earth. The Earth-Sun's distance is called 1 astronomical unit, which is 150 million kilometers, right? So this is about, or it is also called an astronomical unit, 1 astronomical unit. So this one is when it's further from the sun, the aphelion, it is 1.1 astronomical unit, and the perihelion, when it's closest to the sun, it's about 0.89. So it's approximately, the average you see is about 1. So it's about the same distance from the sun as the Earth is, and it has an orbit, which you can see over here. This is your orbit PN7. You see that it's actually kind of going along with the Earth. So the Earth over here, the orbit of the Earth is this blue orbit, okay? The blue orbit is the Earth. So you can see that this object was discovered sometime in August, right? But before that already, this object, while this is the Earth, this object is the one which is going along with the Earth around the sun, right? So it's going along with the Earth around the sun, and it's going to do this kind of thing. So this is this PN7. So in principle, there was a lot of noise about it. This is the object. You can see it's quite an irregular object, not exactly spherical shape. This is this thing. And let us see what is the difference between the moon and this secondary moon. So the moon that we have, it actually goes around the earth, right? And the earth goes around the sun. So in that way, it goes around the sun because it's going around the earth and the earth goes around the sun. So in that process, it goes around the sun. But this object, which we actually see, it is not going around the earth, okay? It is only going around the sun along with the earth, right? So it kind of accompanies the earth around the sun. So it's what we call a quasi moon, okay, or a temporary moon. It is rather, it's not even a moon because it's not under the gravitational influence of the earth. It is under gravitational influence of the sun because it's going around the sun, but it does not go around the earth, right? And therefore, this object, it actually it will go along with us till about 2083. But in principle, we would not call it, I would not call it a second moon. It's kind of an accompanying to the earth. So there are a few known objects nowadays with the kind of telescopes we have. These objects, see, are not very bright objects because these do not emit light of their own. They are basically reflecting light, right? So, but nowadays with our telescopes, since they are so specialized and so good at detecting objects, you have a whole bunch of other objects. For example, 164207 Cardia, all these are different objects which have been discovered. So there are many such objects which also go around this thing, and these are these quasi-satellites. And therefore, we know that many of these quasi-satellites do exist, which are going around the sun along with the earth, but are not the earth's moon, right? So in principle, obviously, to make a big noise on the news, it is good to call it the second moon. But in principle, I would say it is not a second moon, right? But so these kind of objects, they go around the various orbits around the sun. In this case, it's around this thing. So other than with this was done with pan stars, but this year we have another telescope which is coming up, which is the Vera Rubin telescope. This is an 8.4 meter telescope. If you remember, that was 1.8 meters. This is 8.4. And this one has the world's largest digital camera, which has 3.2 billion pixels. And it's going to conduct what is called the Legacy Survey of Space and Time, where it will keep looking for such objects in the sky. The telescope is already ready. The picture which you see is a real picture of the telescope construction. You can see it's already ready, and it's already had its first light. And very soon, especially in 2026, we'll be looking forward to a lot of discoveries which will come of this similar kind, like we had for PN7, from the Vera Rubin telescope, because this observatory is going to detect many such more objects. So that's our first thing. But now it's very important that I talk about the most popular story of this year, which I'm sure all of you have heard about, and that's about 3I Atlas. Okay, now look at this image. This is exactly how these objects are detected. So what you do is you're looking at a part of the sky and you see this object which is moving. Okay. There is a citizen science project which is based on a software called Astrometrica, where you actually look for asteroids, which are possible things which can hit the Earth, right? And they actually look for it exactly using this. So they use data from pan-stars, or there's something called Zwicky Transient Factory, or there is what is called the Catalina survey. There are various telescopes from which you can get data. And what you basically do is you take images of the same part of the sky. Okay, you just keep looking at the same part of the sky, but with that you try to detect a fast moving object like this. So this fast moving object like this over here is moving fast because it is close to us, right? The stars in the background do not move so fast because they are far away from us. But this object is close to us and it's moving in this way. So there is an asteroid search campaign. You may be aware of it. It's a citizen science project where you are actually given these objects. Obviously, they use software to look for such objects, but there could be discrepancies in the software due to which they cannot detect such objects. And therefore, they also share it with citizen scientists who can actually look at these images. They give you, say, 5 images of the same part of the sky, and you have to look at it and stare at it and check whether you think something is moving or not moving, right? And since this is done by a wide range of people all over the world, it kind of, other than the software, you kind of doubly check if your software has missed out something, right? So you can catch it. So 3I Atlas was discovered in this way. This is what is called an interstellar visitor. Okay, this object, I'll show you why we call it an interstellar visitor. It seems to have come from outside our solar system. Okay, now we have with recent this is the third such object, and therefore it's called 3I. 3 is because it's the third, and I is the interstellar. The telescope which is doing this is called the Atlas telescope, and therefore it's called the 3I Atlas. Okay. Now this guy is the third one. The first one which was found was called Umama, which was in 2017. And then there was another one found, which is 2. This is 1I because first interstellar Umama, then 2I, second interstellar, it's called Borisov. And then this one is called the 3I, which is Atlas. Okay. So these are asteroids, and this one is a comet. So Umama is like an asteroid, and these two guys, Borisov and 3I Atlas, are comets. So what is Atlas? Atlas is basically, we know that there is always, like the way dinosaurs were eradicated, you could always have the impact of an asteroid which can actually, finish mankind on the earth. And therefore there is what is called the Planetary Defense Coordination Office, which is run by NASA. And they actually look for such objects which are potential threats. So there is a telescope called the Asteroid Terrestrial Impact Last Alert System, the ATLAS, which is in Hawaii, which is a robotic survey system. It scans the sky and looks for this. So these are the planned ones in orange, and there are active ones. There's Pan-STARRS, there is ATLAS, there is SST. These are the ones which are already running. And then there's some which are also being planned. So what they did is that in the case of this one, you can see that this initially it was catalogued as a comet. Okay, and and what was very interesting about this thing is that the way it came into our system, it had a very widely elongated path. I'll show that to you, which indicates that it's not from our solar system. So I'll show that to you in the next image. So this is the Atlas telescope, okay, which I was talking about. We'll run through it. And this guy has a very strange orbit. And then there was a lot of noise about this because there was a Harvard astronomer called Avi Loeb. And what Avi Loeb actually declared, he actually published a paper saying that this object is an alien spacecraft. Okay. And basically this is because, we'll come to it, but this object has a very large velocity. I'll show that to you. And therefore from its behavior, they thought that this object, that's what the paper went, that this one is a interstellar, it's some kind of alien spaceship. Okay. And therefore, so you see this object is coming in like this. It has a small size. It's something between 450 meters to 5.6 meters. It moves at a crazy speed. The speed is 68 kilometers per second. Can you imagine? It's moving at a speed of about 68 kilometers per second, which is a crazy large speed. And when it leaves our solar system, it's kind of moving through our solar system. It's going to go with about the same speed. It's on a danger to the Earth because it's not going to come closer to us than 270 billion kilometers. It's going to be further away than that. But this guy is coming with a crazy speed. Okay, so you see how this thing is moving through our solar system. It made the closest approach to the sun in October, and this was the object. So this was a very interesting object. If you Google, I will show you, you'll see there's a lot about it. The previous one was Umama, which I spoke to you about. This is like an asteroid thing. And this was the first one which was done. The second one was Borisov. This is Umama Borisov. So basically, we know that these are interstellar comets because these objects come in at very high ellipticities. They don't come in with, the solar system we know is a planar object, right? All the planets are approximately on the same plane. This thing comes at a very high ellipticity, and in this case, a very large velocity. So obviously, everybody was very interested in studying this object. This is an image from Gemini South in August, where you can see that it's clearly like a comet. It has a coma, it has a tail, and this is how it looked in August. And it was, so all the studies, there were studies made with Hubble telescope, with James Webb telescope, with Chandra, with all the telescopes, almost all the telescopes in the world, all of them looked at this object specifically because it was this, very studies show that it is undeniably a comet. Okay. And then people also did spectroscopy to actually see what are the contents of it, the chemistry. So it has cyanogen gas, it has diatomic carbon, and these are typical constituents which are there in comets, right? So, but then while there was all this going on, we 3I Atlas, you saw it, it came to a trajectory which got it close to the sun, and then it moved out. But then in about early, in about this thing, it actually seemed to be disintegrating. Okay, so they actually noticed that this fragile IC nucleus was actually disintegrating and dissipating. Okay, so this object which we have, we are sure, quite sure that it is some kind of a comet. Okay, and it obviously gives us evidence that even in other planetary systems you can have carbon, cyanogen, these kind of carbon based things. The fact that it disintegrated, it actually shows us that how fragile these objects are. It was a fleeting guest, a snowball from solar system. From a star system we'd never know, but it reminds us that it's part of this thing. So if you see that, even now, if you check on this thing, you will see that astronomers will continue to track this into 2026. So in 2026 also, even now if you Google, I've got a link here. Yeah, I'll show that to you. But you'll see that even in 2026, there are definitely going to be lots of new snippets on 3I Atlas, because people are still very, very interested in this object. But from all the studies that we have till now, it appears to be that it's a comet. It's definitely not a spaceship as what was proposed by Avi Loeb. So if you actually look at the news also, even in the news, if you can see, you will see that this object, if you see 3I Atlas, these are various NASA missions which are trying to actually track this object. And you can see, we don't have the time today, but this is the discovery images, and then you can see Hubble, James Webb, etc. A lot of work has been done in actually trying to study this object. So if you can go through, there's the Europa Clipper, there is various missions which are actually trying to study this thing. This is SOHO and Stereo and various missions which are actually trying to study it. This is Lucy. So I'm sure even in 2026, you are definitely going to see a lot of, lots of things coming up from this. That's for sure. Okay. So are we back with my PPT? Can you see my PPT now? Yeah.
Yes,
Yes,
ma'am.
yes.
Yes.
Okay, great. So now these are our two solar system kind of objects, which included second moon and 3I Atlas. And now we'll go to something let's move on to stars. So in stars, one of the most, you couldn't see the second screen, Narayan Bajaj. You all couldn't see the screen which I showed you for
Yeah, just
NASA?
before this slide, we could not see those pictures actually.
Oh,
Yeah.
okay.
Only the presentation part was seen.
Okay. Okay, no problem. I'll just, I can show that for a minute, no problem. I will, let me do this 1 minute. Yeah, so I can show you this. Can you see the screen now? This Chrome screen? Can you see the
Yes,
Chrome?
ma'am. Now it is visible.
Yeah. So
Yes,
this is
ma'am.
just from the net. You can have a look at it. So like I said, 3I Atlas is very much, there's a lot of observations, lots of work going on in. So you can see that even NASA missions, the ones I was talking about, Hubble or James Webb, or even there's even the Lucy spacecraft. There are lots of studies still being done with various telescopes, etc., to actually study this object. Okay. So I'll now stop with this, and I will go back to sharing my other one. This you can't see, right? So I will, 1 minute, I'll just give you the screen. So now can you see Betelgeuse? You can see Betelgeuse?
Yes.
Great. Okay. So now we are coming to number 3. Number 3 is now a star, right? So one of the biggest discoveries which happened this year was related to Betelgeuse. Most of y'all, I'm sure you know how to recognize Betelgeuse. You know Betelgeuse in the sky. I'm sure the first people who start doing some observations, you'd learn how to identify Orion, right? Orion is the constellation. Even now, if you go out in the sky, you'll see Orion out there. Very easy to identify. 3 stars over here, and you have these guys are here. So this is Orion, the hunter. This is the belt of the hunter, the shoulder, and this is Betelgeuse, okay, which is a red giant, okay. This star is huge. If you see here, it's compared with the orbits of the planets of our solar system. So you can see that Betelgeuse is kind of larger than even the orbit of Jupiter. This is the orbit of Jupiter, okay, not the size of Jupiter. So you can see that the size of the star, if you see, this is the Earth's orbit, this is Jupiter's orbit. This star is much larger than even the size of Jupiter's orbit, okay. And this star is a very bright star. So if you go out after this talk, you go out in the evening, look up at the sky and you find Orion, you will definitely be able to see Betelgeuse, right? So Betelgeuse is a very well-known star, very well this thing. Okay. Now, recently what happened is, I like this story very much because this actually shows you how science develops, okay? How is the working of science, okay? So this is Betelgeuse, like I told you, you'll see Orion in the sky. It's a reddish star, it's a red supergiant, so you'll see it red. The blue star over here is Rigel, which is about the same brightness. Okay. Now what happens with this Betelgeuse? It's a red supergiant star, and this star is actually a variable star. Okay, it changes its brightness. Okay, and it has a mass of about 17 to 19 times the mass of the sun, a radius of about 900 times the solar radius, a luminosity of about 100,000 times the solar luminosity, and it rotates at a period of 17 years. It's about 10 million years old. Okay, it's a young star. By astronomy standards, it's a young star. But in astronomy, if you know any stellar astronomy, you know that the age of the star is inversely proportional to its mass. And therefore, massive stars, they basically die out very fast. Okay, massive stars die out very fast. And therefore, what happens is that this star, because it has a mass of about 20 solar masses, right? Therefore, even its age is very little. It's only about 10 million years, right? But it's already become a red giant, right? A red giant phase is a later phase in the evolution of stars. So when stars are born, for some time they are kind of constants, which are called main sequence stars, and later on they become what are called giants. Okay, and this is a red supergiant star. Okay. Now, what happened, if you see the star is a big star, it's a very big star. If you know any of these other stars, for example, Sirius is the next brightest star after the sun in our sky. Sirius is much smaller. If you see Rigel is also much smaller. Betelgeuse is a huge star. It's a very big star. Okay. But it's variable. So if you were to see it, this is between 2009 to 2018, you'll see a nice periodicity, right? You can see a nice periodicity or change in brightness of the star. So what was actually found is, if you actually look at this change in brightness, it approximately has 4 periods, okay? There's one period which is about 2,200 days, one period 420 days, one period of 230 days, and one period of 185 days, okay? So, but you'll see that in real stars, what happens is these don't exactly add up in a perfect way, right? If I were to add 4 sinusoidal curves all with the same period, I would not get such a, what you see, these points, observation points are obviously, they kind of indicate a sinusoidal thing, but not very perfectly. That is number one, because it depends upon when you got your observations, what are the kind of observations. And then even more important, that many of these stars, like our sun itself, they also have sunspots, okay? And these are huge sunspots. So you could have a variation in the brightness also happening because of sunspots, and sunspots are kind of erratic. They can appear at any part of the star and move at any time. So Betelgeuse is variable. And why is it variable? Because Betelgeuse is a pulsating star. What do I mean by a pulsating star? It becomes big and it becomes small. It pulsates in its size, okay? It becomes big and small. This is the specific kind of stars, which are these giant stars. They pulsate, change their radius, okay? So that's the star, it's actually pulsating. And so the question was that, remember I showed you there are 4 periods, 2,200, 420, etc. These are these different periods which are there. And the question was, so that's normal. You basically see that the star is a variable star. What's the noise? Now, first of all, there was a big noise with Betelgeuse in 2019. That's because suddenly in 2019, Betelgeuse became very dim. Okay, it became dim in the sense it suddenly, in terms of magnitude scale, it actually almost reduced by its brightness reduced by a factor of 2.5, and it dropped almost by 1-2 magnitudes in brightness. You can see this curve over here where there's a fall in brightness. So people in 2019 got very this thing about it, and they said, God, this star is going to go out supernova. Okay, so we know that for a star to fuse hydrogen to helium takes about 10 million years, which it's already done because the star is older than that. Now, if it's fusing helium to carbon, it will do that for 500,000 years. After that, if it finishes carbon to neon will be about 600 years, neon to oxygen 1 year, oxygen to silicon 6 months, silicon to iron 1 day. Okay, and that's when it's going to go boom as a supernova, right? So the question was, is it that the star is going to go supernova? Why did it suddenly go dim? People thought it was kind of a lull before the storm, right? And so people were wondering what's happening, when is it going to go supernova, right? But by calculations, people thought that if you look at this, it's about 500,000 years, so at least 100,000 years, something of that kind it would take to get supernova. But if it goes supernova, it's going to be as bright as the moon, as a gibbous moon, and it could even cast shadows on the ground. But the question is, what if Betelgeuse actually went boom? It went this thing. Actually, in principle, we don't need to worry. If Betelgeuse goes boom, it's so far about from us. It's about 130 parsecs away from us. Okay, so therefore, because of that, there'll be a shock wave created when it goes supernova. But by the time it reaches us, it will stop outside the Earth's orbit. So it's not going to do anything to us. If we have a star which is within 10 parsecs and then it goes supernova, that's going to be fatal for us. But this is not exactly going to be fatal. So we are safe. But then what happened is that there were a whole bunch of papers as to what's happening. Is it going to, some estimates showed that the star will at least take 100,000 years to go supernova. So this is not a size of, so the question was, why was Betelgeuse dimming? Okay. And then there were observations done to show that there was no fall in temperature. The temperature of the star was the same. It's not become cool. And that's when a possible explanation was dust. Okay. And basically there were many telescopes to try to observe it. And basically what they found is that there was episodic mass loss. In the sense, this star, because it's a giant, in episodes, it actually throws out its mass. You see these shells. These are real images of shells in which it can actually throw out mass. And this is a real image of the star using the ALMA telescope, the Atacama Large Millimeter Array. And you can actually see that there's a lopsided shape and there's a huge bright spot. And this is another image using the VLT, where you can actually see that you have this. And here you can see, this is again with VLT, where you can see in different periods from January 2019 to March 2020, how there was a difference in brightness, okay? And therefore, this was the possible theory, is that there was some episodic mass ejection from the star. And then when it hit this outer part, it actually created a whole amount of dust. And that dust came between us and the star, which actually led to this fall in brightness. So there's an article, I'll promote my own article. This is in Resonance on Will Betelgeuse Explode, which was published in 2020. Okay, so you can have a look at this article. You'll see much more details about this over here. But then the story continued. After that, when people continued observing Betelgeuse, this is what is called the Great Dimming. Suddenly, Betelgeuse again became bright. Okay, so probably the dust had moved off, the dust cloud. These are various other telescopes which continued observing it. And you can see, this is called the Great Dimming. After the Great Dimming, again you have the star coming back almost to its original brightness. Okay, so again the star becomes bright. These are in two different filters. The star is again become bright. So by 2025, you can see the star has got its almost normal brightness. Okay, so then, but then what happened is that there was a slight this thing in the pulsation. Okay, so it was missing its 420-day pulsation. Okay. And then people try to study from the pulsation periods. The question was, which is the primary pulsation period? So this paper by Sao, they assumed that 2200 was the primary pulsation period. If this is the primary pulsation period, then the problem is you can use the pulsation period to estimate the mass or the luminosity of a star. okay? Because these stars have a mass, they have a luminosity temperature, luminosity period relation. So then if 2200 is the primary period of the star, then in that case, they predicted that the mass of the star was such, you can see the mass, it's about 10 to 12, and if it was this, then this star has already gone supernova. This star is actually about it's far from us, so the light will take time to come to us, but probably it has already gone supernova. So if you actually see, you would actually see, the question was, if they took this 2200 day periodicity, then the star has already gone supernova. So you'll actually see a lot of estimates which said that. But then there was another paper by Joyce et al. Which says, no. 2200 is not the primary period. The primary period is 420 days, right? They used other observations to actually this thing. And then they come up with even a more interesting theory. This is by this group McLeod, who said that Betelgeuse seems to have a companion, okay? And most probably there's a companion star. But the question was, if you take an image of the star is so bright, how are you going to look at the companion? Okay, so they tried to detect this companion. Very difficult to image it because the star itself is super bright. It's a very bright star. So how are you going to detect the companion? And you can see there were various images taken of the thing, but they could see the companion. They used Hubble Space Telescope, the Chandra X-ray telescope, but they could not find this thing. So they said, if there's a companion, this has to be some low mass young stellar object. Only that can give you this thing. And that's when this is Steve Howell, okay? And what they used is they used this telescope, which is the Gemini Naught telescope, 8-meter telescope, and they used a very special technique in astronomy, which is called speckle imaging. So why do stars twinkle? We know that when the light comes from the star, because of the atmosphere, it gets shifted. The position gets shifted. And that shift is what we call twinkling. But if you were to take short images, very short images, which are smaller than the period in which the turbulence in the atmosphere moves, you can get images. So ideally speaking, because of the atmosphere, if you had a single star, you actually see the image moving in various points, which is your twinkling. But speckle imaging, you take short exposures. Look at these things. You take very short exposures of the star, and then you add up these. You do what is called lucky imaging. You choose the best images which come in these very short things, and you add them up. So what they did with this 8-meter telescope, 8.1 meter telescope, is that they took short exposures, 60 milliseconds, 6,000 of them, and you took 6,000 10 millisecond exposures. These are two different filters. And you take these exposures and you stack them up. And then when they stack them up, they actually got a detection. So the detection is what is we call a 1.5 sigma detection. It's not we generally, when we detect objects, we wanted to at least have a 3 sigma detection. But this was 1.5 sigma, and they actually got this. I'll show you the image. And this is the image they got of Betelgeuse and its companion star. So most probably the dimming event happened because this companion star, if you see, I can show it to you. It is kind of within the envelope of Betelgeuse. So it is going around Betelgeuse. It has a mass of about 1.4 times the mass of the sun. It's going around over here, and probably when the dimming happened, it came in and caused this, dust cloud to happen, and it's going around over here. And this one is what is causing this period, okay, which is the pulse, which is the period which we have. And so this one is the 2200 day period. The other one is the 420, which is relating to the pulsations. So therefore, this is the thing in the HR diagram. This is, we don't have time to talk about it, but it is about the same age of Betelgeuse. So it formed along with Betelgeuse about 10 million years ago, but it has a much smaller mass. It's 10 times smaller than the mass of Betelgeuse. It's only about 1.4, 1.6 times the mass of the sun, while Betelgeuse itself is like 17, 18 times the mass of the sun, right? So it's about 10 times. This one is 10 times less massive than Betelgeuse. Now, Betelgeuse is actually means hand of the giant, and this thing is the companion, and that's why it was given a name Sivara, which means the bracelet. The bracelet of the giant, and that's the one. So what's happening is that the next predicted elongation for this stellar companion is supposed to happen in 2027, November 26th. And that's when people hope to again run spectral imaging and find this companion at this close proximity. Okay, so we have to this thing. 1 minute. Yeah. So that's when they hope that they can again observe this object and detect it, because that time this object is going to be at a larger elongation from Betelgeuse. Okay. So it would be easier, hopefully, to observe it.
You
Okay.
are now connected.
So it'll be easier to observe it, and we'll be able to do that. Right. So, so that's our interesting discovery number 3. Okay. And now we'll come. Okay. So Betelgeuse, actually, I wrote 2 resonance articles. The first one was the one I showed you, and the second one, which has also got accepted already in resonance, and you'll hopefully be able to see it. You can find it online, and this is the second article again describing the beetle buddy hypothesis. So do have a look at this article, and it'll give you much more details, because today it's kind of in a hurry. Okay. Now, the last one I'm going to talk about is on galaxies. So from stars, we are now moving to galaxies. And this is a very interesting new result which has been come with James Webb Telescope. So with James Webb, you basically had, and the good thing is that this is done by Indian astronomers from the National Center for Radio Astrophysics, which is located in Pune. Okay. And what they basically did is that typically we know spiral galaxies, they take time to form, okay, because a grand spiral is a very specialized kind of a structure. So if you actually look back time, if you look at, that light has a finite speed. So therefore, when we're looking at objects which are further away, we are looking back in time, right? So if you look at objects which are at a distance of 11.6 billion years, right? This is light years. You typically do not expect to find spiral galaxies, because these galaxies at that time, they are, they don't form. We assume that such things cannot form that early, right? While we assume that at closer present day scenarios, then we form spiral galaxies, because spiral galaxies have a very specialized kind of a structure, right? Which we assume that in the early universe, we couldn't have formed such specialized structures. Okay. So that is what our understanding is. Now here, this is the group, which is Rashi Jain, PhD student. This is a supervisor, Yogesh Varadekar. And both of them, they were actually, like I said, ideally speaking, you should not be seeing spiral galaxies in the distant past, when the universe was very young. But they actually found a galaxy which is actually dating back to when the universe was only 1.5 billion years old. The universe was very, very young. Okay. And they found this object which actually has clearly defined spiral arms, a central bulge, disc-like morphology, and things like that. They named it Alaknanda, which is a river in Himachal. And what is very interesting for you to appreciate it is how would they get so lucky to see this object? This object is a very high redshift. It's very far away from us. But what happened is that it lies behind a very massive galaxy cluster. Okay, this galaxy cluster is called Abell 2744. Now, what's very interesting is that that through Einstein's relativity, we know that gravity can bend light, right? And that's exactly what a lens does. A lens actually bends light, right? And because the lens bends light, therefore, when you look at an object, right, from a lens, you can actually focus it to something or, do something like that, because the lens has bent the light to either converge it or to diverge it. So it is either going to behave like a convex lens or a concave lens, one of the two. Now, gravity also bends light, and therefore gravity also behaves like a lens. But obviously, if you want a good lens effect, then your gravitating body should be very, very massive, right? So in this case, supposing you have a galaxy cluster, right? This is not one galaxy. This is a cluster of galaxies, okay? So it's obviously going to be super, super heavy, massive. And therefore, what happened by chance is that this galaxy, it lies behind, supposing this is Alaknanda, there is a galaxy cluster. So ideally speaking, we would have not been able to see it, right? Because it's very faint, it's very far away. But this galaxy cluster between us and that behaved like a lens, and it actually gave us this great magnified image, right? Lensed image of this galaxy so that we could observe it. And therefore, you actually see this galaxy because of this great coincidence of this galaxy cluster being there. So if you see, this is the field in which they saw it. Here you have this object, and if you zoom in it, you can see it over here, and it's a well-defined spiral galaxy at very early universe. This obviously got people really confused because we do not expect to find spiral galaxies so at such an early stage. It is about 1/3 the size of the Milky Way. It's a small galaxy, not a very big galaxy. And the James Webb images is taken with 21 different filters through which you can actually estimate its redshift. And this also very interesting about this galaxy is it has about 10 billion stars. But what's more important is that it has a very active star formation rate. The rate is about 60 solar masses per year, okay, which is about 20 times that of the Milky Way, the star formation rate. So that means at this early stage of the universe, it's actually forming stars at a very, very fast rate, okay? And it has a mass of about this much. So this is a very interesting object, which now, obviously, this is not an isolated object. Many such objects have been also found with James Webb telescope, and therefore galaxy formation theories need to be revised, and even the formation of spiral galaxies and structures like that needs to be this thing, because Alaknanda suggests that the universe was much more orderly than astronomers believe. Also, to add on to James Webb, you also have these other objects which have been observed with James Webb, which are called little red dots, LRDs. And these are also galaxies, these are objects which are again the same period when the universe was about 1.5 billion years. And people thought that these are probably dwarf galaxies or dense star clusters, but they're so bright that now when they took the spectra, they actually see that these are they are like supermassive black holes, okay? So people are actually now revising their idea of galaxy formation because we have these supermassive black holes at such an early universe. We know that supermassive black holes behave like seeds of galaxy formation, but how exactly these play a role in the formation of galaxies has to be further studied and discovered. So that's also a lot, which is a lot happening because of James Webb and the various discoveries with that. So I will conclude with this, that essentially astronomy is a field where it's technology driven. The more telescopes you have, the more discoveries you would make. So for example, aware of, there's James Webb, which is now recently operational, already told you about. There is also the Gaia, which is by the European Space Agency. And then there are loads of more ground-based and space-based telescopes. And as we have these much more specialized telescopes, obviously the kind of discoveries that people are making with these telescopes and the kind of objects we are going to see obviously make it very exciting. Not just 2025, but even 2026 is definitely going to be very exciting with all these new telescopes and discoveries and different kinds of objects that we are getting to see. So I will conclude with this. Happy New Year to everybody, and I'm sure there's a lot we are going to be able to actually see. So I had a little stupid
Yeah. Thank you,
thing.
ma'am.
Okay, baby, you can see.
Yes, yeah. So for such an insightful talk, and actually, I think 2025 has been really a year with a lot of new discoveries and inventions, especially using telescopes like James Webb. And ma'am, you have presented it so beautifully to us. Makes us more created more interest in astronomy. So with this, yeah, let me open the session for question and answers now. So if you have any questions, you can ask to all the participants.
Hello, madam.
Yeah.
I actually want to make it clear about or myself that you told that in Betelgeuse it was dim due to the dust which was emitted. Is it really dust or some kind of plasma as it is emitted by our sun?
No, it's dust because for the dimming, the plasma will not cause that kind of extinction. Extinction, you basically need something which will absorb the light so that you can have that kind of dimming, right? By about 2.5 times less brightness. So it is not plasma, it is the plasma got ejected and then that caused the dust in this outer region of, of Betelgeuse, which then caused the dust, which is, so
Okay.
it's kind of, it's plasma causing dust kind of thing. Yeah,
Okay. Thank you. Thank you.
yeah.
So, ma'am, I think this is the same way how the new stars are born from the dust clouds. Same way, the Betelgeuse, part of the Betelgeuse, is just gone thrown away. Is that the way it happened and it collected together?
No, not at all. So
Okay.
actually, when young stars are formed, it's basically formed in giant molecular clouds, which are very cold. It has a
Yes.
temperature of barely 10 Kelvin, okay, 10, 20 Kelvin, and it will be dense, and you have what is called gravitational collapse, means gravity causes it to collapse in its own weight, right? And that's when you actually form a star. But in the case of Betelgeuse, this is a supergiant. So this is almost the outer region of Betelgeuse has a temperature of about 4,000 Kelvin, right? It's very hot. I mean, it's hotter than 10, 20 Kelvin. So you will not have any gravitational collapse taking place in the outer regions of Betelgeuse. No, so that is different. That is different. The Betelgeuse outer region is much hotter and you did not have gravitational collapse. You don't form stars like that. No.
Yeah.
Yeah.
Okay. Oh, any questions? Kulkarni sir, आप unmute कीजिए please. Sir, Kulkarni sir, please unmute. Kulkarni sir, can you hear me? Please unmute yourself.
Kulkarni sir, you are muted.
Actually, there's another person who's asking a question, no? Samantha.
Okay. Yes, Samantha.
Prajwal, yeah.
So, ma'am, if we discover more stars which have companions, so why do more stars have companions? Like, why do they form two of them instead of just one?
Yeah. So actually, that's a very interesting question. Thank you. That's a good one. What is actually observed that stellar multiplicity is kind of proportionate to mass, in the sense massive stars often have companions. Generally, a massive star has a companion, and generally low mass stars do not have companions. Okay, and that explains why if you look at old astronomy textbooks, they will write and tell you, oh, most stars are binaries. Okay, and that's basically because when they observed bright stars, right, bright stars are obviously more massive, and then when they looked at bright stars through telescopes, they often discovered that it was a double star. So they thought that most stars are binaries, but it's actually not true, because like I told you, massive stars are often binaries, but low mass stars are not binaries. So this is what is called an observational bias, because through our observations we are more likely to look at more brighter stars. More brighter stars will be more massive, and these more massive stars will most probably have companions. So we may assume that all stars have companions, but what we see is more massive stars have companions while low mass stars do not have companions. So this is an important piece of observation. But in terms of theory, we do not know very well how does this theory work. Why do we need a companion when we are forming more massive stars? We do not know that very well.
Yes. Thank you, ma'am.
Yeah, welcome.
Kulkarni sir.
Yeah, I just wanted to wish everyone a good 2026, and we had a lot of activities in 2025. I'm looking for at least doubling or tripling the number of sessions and also activities. Compared to 1924 or 2024, 2025 was much brighter, and I'm sure 2026 will also be brighter with the cooperation of all the other people. We are thinking of making zonal representation, that is, instead of only one NASNI, there will be NASNI East, West, North, South, Central, and Northwest, and we want volunteers to come forward and conduct many activities. The routine activities of NASNI will continue, but in addition to that, we expect every zone to do at least 20 or 25 sessions throughout the year. So typically, two sessions other than these two sessions that we have. We hope people will cooperate. We expect everyone to attend regularly. Attendance of 21 out of 80 is not a very encouraging thing, but it's okay. People may be busy celebrating the new year and things like that, but it doesn't matter. So that's all. Nice to see
I
Priya
think,
on
yeah, we have a
screen after
question
a
by
long time.
Radhika. Yeah.
Hello, good evening, ma'am.
Yeah.
Ma'am, I want to ask that you said that we have Betelgeuse has a companion. So can we take it as a moon? Like we are our Earth has a moon. So
No, no,
can
no. It's
we?
a star. That companion is a star. It's not a star. It's a star. So it's a binary star. Yeah. It's not a moon. A moon is not a star, right? It does not emit any light of its own. The moon just reflects light from the sun. But the Betelgeuse companion is a star by itself. But it's
Ma'am,
a young
then
stellar.
it's is a मतलब इसकी प्रॉपर्टीज हमें मतलब emit light emitted करती है ना फिर?
हाँ, तो वो एक्चुअली एक तारा है, वो प्लैनेट नहीं है, सैटेलाइट नहीं है। सैटेलाइट या प्लैनेट्स क्या होते हैं, उनमें से लाइट नहीं निकलता है। मीन्स उन लोग जनरेट नहीं करते लाइट, उन लोग रिफ्लेक्ट करते हैं लाइट, जैसे मून करता है। मून का अपना कोई एमिशन प्रोसेस नहीं है, वो सिर्फ रिफ्लेक्ट करता है। लेकिन ये जो है, दिस इज अ स्टार, ये एक स्टार है। इट्स अ यंग
Ma'am,
स्टेलर
then what
ऑब्जेक्ट।
about its 420 days concept? Can you please explain me
So the
again?
420 days is from pulsations. वो जो pulsations का जो हो रहा है ना, यानी कि size जो change हो रहा है, वो 420 days का है. And most probably this 2200 days का जो period है, ये is happening because of this companion. तो ये companion के वजह से जो change in brightness हो रहा है, वो 2200 days is because of the companion, while 420 days is because of the pulsation.
Okay, thank you, ma'am.
तो एक्चुअली उसी में कंफ्यूजन था कि ये 2200 डेज उसी को अगर आप पल्सेशन पीरियड करते हैं तो फिर आपका मास अलग हो जाता है, तो फिर आपका सुपरनोवा का जो टाइमिंग है वो अलग हो जाता है. यू अंडरस्टैंड राइट? हाउ सून
Yes,
विल इट
ma'am.
गो सुपरनोवा? दैट विल बी डिफरेंट.
Okay, thank you, ma'am.
वेलकम.
Madam, if as per some thoughts, if already explosion has been happened in the Betelgeuse,
Yeah.
and it will take so many years the information reach to Earth, then
Correct.
what we will see after some time? We won't see this Betelgeuse as it is after that.
Yeah, so that's the problem with the distance, right? So for example, if the sun also switches off, the sun is 8 light minutes away from us. So we will get to know that only where after 8 minutes if the sun switches off, right? So this star also, so that is basically happening because of the distance of the star, because light is taking finite time to reach us, right? So we will get to know only too late. You know, in the sense, Betelgeuse is about 700 light years away from us. So we will only, if it's supposing today it goes supernova, right? We will get to know only after 700 days. That's the problem. Yeah, we
Ma'am,
can't, and we
sorry to
cannot get information faster than that. Ha, bolo.
Ma'am,
Yes,
sorry to interrupt,
no
but
problem.
what is the concept of 1.5 sigma detection? I can't understand that
Okay.
thing.
Yeah, very good. Thanks. That's a very good question. So in science, what we have is you can have a signal, right? And you can have noise. Noise is, for example, you'll have, supposing you're taking a measurement, you will get a slight variation in the measurement, right? Which is called noise because of the variation, because of errors, because of coming of errors, right? But supposing if you detect something, there's a signal. Generally, a signal, if it is 3 times the errors, which is sigma is the error, the standard deviation. Okay. So generally what we do in science is that for a signal to be considered respectable, you know, to be considered a signal enough, we need it to be 3 times more than the level of the noise. Okay. Then I can say it is a 3 sigma detection. Okay. So if you remember when I showed you the image of Betelgeuse and its companion, Betelgeuse is much brighter, the companion is very faint, right? So if we compare the brightness of that companion to the brightness of the background, udhar ka jo noise hai in that area, then the brightness of this companion is only 1.5 times of the brightness of the background. You understand, of the noise. And therefore, in science, generally 1.5 sigma is not considered, valuable enough. But the problem is that when they did this work, they had very well predicted that where will the companion lie, what is the size of the companion, where is it going to be, various things about the companion. And therefore, though this is only 1.5 sigma, people are taking it as, a thing that can be, what do you say, considered as a detection, because it was well, because it was what was expected, right? So it ideally it should be 3 times the noise, but in this case it's only 1.5 times of noise. But it is this. So what is actually planned is that, in 2027, when again these two are going to be far from each other, the Betelgeuse and its companion, they'll be again far, so it'll be easy for us to detect it. That's when people want to again do fresh detections, which are better planned, where hopefully we get it with a better level of, it is called level of significance, right? A better level of significance. That's what we hope to get in 2027.
So there's one question here in the chat box. Let me just read it. The question is from Bharti and about binary system. So she's asking, if one star of the binary system explode with the second one, will the second one also explode even if it is younger star?
Yeah, thank you. That's a good question. So actually that tells us the fate of this poor star, which is Betelgeuse's companion, because Betelgeuse is actually going to go, this is what is called a young stellar object. It's a young star which has not yet formed. Okay. And therefore, what's going to happen with this poor star is that Betelgeuse is going to go supernova before it actually becomes a star. So this will be a star which never becomes, which never becomes a star, because Betelgeuse is going to go supernova before it finishes its thing. Yeah. So this, what will actually happen is Betelgeuse will go supernova because it's finished its nuclear fusion. This star will not yet be formed as a star also, and it will kind of get engulfed by Betelgeuse. That's it. Yeah. So it has a sad future.
Sad future. Ranjita ma'am.
Thank you so much. It was really a very wonderful talk, and I really enjoyed it. And as the year also is coming, today is the last day of 2025.
Yeah.
So I also that is the best part. No, we are ending with our very interesting talk and our passion. No, we love this group. I love NASNI group, and to hear something nice on this last day of 2025 is also I feel very good about it. And I also wish everyone a very happy new year, very happy 2026. And I hope we will also come forward with many new things, many new creations. And I'm sure Hemant sir also has many things in his store. He will also provide us with many interesting topics, he will give us surprises. That's all I want to say. Thank you so much, everyone.
Yeah, thank you, ma'am. Priya ma'am, are we going to see any I'm just thinking whether we are going to see any supernova maybe in another 50 years or so.
No, there is one which is Eta Carina. There's another star which is possibly would go supernova. But like I said, no, in astronomy, our errors are, in hundreds of years, which are a little too much for us, not our lifetimes. So we, I don't know, it's a question of luck. But the thing is that very often what we actually more observe is supernova in other galaxies. Okay. So especially now with Vera Rubin telescope, when Vera Rubin telescope comes up, we are definitely going to see many supernovae. So Vera Rubin will give us a lot of supernovae in this thing. I can actually check the number of. So we are definitely going to see a lot of supernovae in external galaxies, right? So the estimate is that we are going to see, what is the number? Okay, it actually says, this is the expectation, that it will actually give us 10 million over 10 years of observations with Vera Rubin. we will discover 10 million supernovae. So is the estimate.
That's
that
good.
we
Yeah.
have. Yeah.
Yeah. Thank you. So, our national president is here with us. May I request Professor Aluwalia to please join us? Yeah.
Oh, yes, I think it's a great way to end 2025. Thank you, Professor Priya, for a
Ji.
wonderful talk.
Thank you.
In
Welcome.
fact, for me, I am a kind of a novice in astronomy. For me, sun and moon were the fascination, not beyond that. But I think this program of a series of talks, and there are 25 talks which have happened in the year 2025.
That's really great. Yeah.
And that has really given a lot of excitement. And yesterday there was a quiz, I participated in that, and I could really score out of 30, 26 marks. So I thought it was a great achievement.
Congratulations.
So I think this is very exciting forum which we have in IAPT. And NASNI actually is a Hindi name for a girl, which stands for small but significant. So that is also a very meaningful name for this initiative of IAPT. Professor Hemant has done. He created a gist of every talk, pick out some beautiful pictures because astronomy doesn't have any dearth of beautiful pictures out of those talks itself. And then he has also provided a QR code of the link of those talks on the pages of that booklet itself. So that if you have missed any of the talks, any of the members who are not able to participate in this kind of a program will be able to, hear those talks again. So it is not that we are small in number sitting here, but we always believe that it is a big resource generation also for the community to come back and revisit those pages and do something beautiful. Professor Arun A.G. Kulkarni, sir, he is always, in a position and in a state of mind to raise the bar of the work which is done. He never feels happy with what we have been doing. So he has now raised the bar to start zonal NASNI, chapters. And I think maybe if somebody can announce to start that kind of a chapter, the best person available to us is from Northeast, Ma'am Ranjita Deka. So, ma'am, please proclaim that today that you are going to have a NASNI chapter in Northeast. And I think that is the great way to begin. And
well, I will try.
yes, because in North, we already have, though we call it as a central thing, which Professor Hemant is looking after. My fascination is really getting further regarding all these programs. Ma'am Priya will also like this idea. I live in Himachal Pradesh. I'm in Shimla actually.
Okay.
So the sky in Himachal Pradesh is wonderful. In your lecture, I heard that Alkananda is the name which has been given to the latest discovery. If we can really initiate astrotourism via or under the NASNI program itself,
Yes.
it will be a great thing, great possibility. And this astrotourism can be in the form of a small NASNI convention, which we can hold for 1 or 2 days at a place where we get clear sky, free from light pollution. We go there for 1 or 2 days and watch sky and listen to some wonderful talks like Ma'am Priya's talk today. It was a very, very scholarly talk, ma'am. I think it was one of the most scholarly talks which I have heard today.
Thank you.
Brought in so many references for us to look forward to, particularly the resonance references, because they are freely available and we can always, download those free of cost.
That's right.
And I was seeing, because you come from a Urdu university, isn't it?
Yes. Yes,
I
sir.
was seeing that you had also given a Urdu name in one of the transparencies to one of the stars which you were showing us.
No, that's an Arabic name. That's an Arabic
Yeah,
name.
that was an
That
Arabic
is
name.
Tivara. I did not give it. That's the name that has been given, not by
Yes,
me.
yes.
Not by me. But it's
But
an Arabic name.
yes, yes. So maybe we would love to hear from you, ma'am, in future
Sure.
the contribution of Arabian astronomers in astronomy, not
Yes.
just Indian astronomy. We can even think of bringing in Indian astronomers in this. So I think that was my joy. I was really delighted. This initiative has been taken seriously. There is no doubt about that. Thanks to Professor Hemant, Professor Reshma Rawat Desai. They are the stars of this program, actually, the names I am actually going to take. Ma'am Ranjita Deka, then Govinda Lakhotia, Professor Anwane. I heard recently one talk which was given in Nagpur in Professor Anwane's department, which was totally devoted to gravitational lensing itself. And it was a wonderful talk which was given then. So I wish if we can also start some kind of a competition now, maybe a photo competition of the pictures taken by the members of NASNI group or of IAPT members. That will be a beautiful addition to the work which we are really doing.
Yes.
As an IAPT president, it's all my pleasure to thank each one of you for this tremendous effort which you have made and enlightened us. Ma'am Priya, I also took some pictures with my mobile ever since I started, and my favorite picture which I can take easily is of Orion.
Oh, very
So, and today it was a part of Orion which you discussed in today's lecture. It was just great. And I can only say, wish you a kind of a supernova success for the next year and wish you a very, very happy new year 2026. For us, 2025 was a great, great year. Let me say like that. I'm very feeling very proud of my community that they really made it a grand, grand success. Goa was the place we visited this time for our convention. Ma'am Reshma welcomed each one of us. And we had a great time there in Goa. And last year I was in Northeast. Ma'am Ranjita hosted me there. That was also again a great visit. This year we are going to be at the national capital for our convention. And last year, Ma'am Priya, we had a wonderful lecture in our convention in Goa convention. That was by Professor Ajit Kambhavi.
Okay.
And it was on the very modern kind of a topic using machine learning to classify galaxies. That was a wonderful thing, the kinds of projects which our students can do at the undergraduate level also.
Yes.
So I think with these words, I wish each one of you, your families, a very happy New Year 2026, a healthy New Year 2026, a joyful New Year 2026. Thank you very much and good luck. See you again in 2026. Thank you.